So in this lecture we will try to give a geometric interpretation of duality. So in the last lecture what we have seen, so given the primal, the optimum occurs at an extreme point where the cost vector can be written as a non-negative combination of the vectors defining the hyperplanes. I mean, this is the hyperplane and this is the outward normal, and it corresponds to the, so if this was some 2x1 plus 3x2, then this is the vector 2, 3. So among all the extreme points, we consider the points where cost is written as a non-negative combination of these outward normals, and that is going to be the optimum. So we saw this in the last video. Starting from this point, we will motivate the definition of the dual and we will try to prove the duality theorem. Okay? So our first definition today would be, see, look at, so in this two-dimensional case, to get an extreme point, we needed two hyperplanes. Look at this point, which is the intersection of 4 and 1. This is not feasible because it does not satisfy this constraint. Okay? We will call such points which are obtained as intersections as intersection points. So in the n-dimensional case, you choose some n hyperplanes and make the constraint to be equality. We are not going to care about the other remaining constraints. So points satisfying equality for some n linearly independent rows from ax less than or equal to b. And we say that these points need not satisfy the other inequalities. So here this does not satisfy this inequality. Okay. Now extreme points are a special case of such intersection points. Extreme points are intersection points that are also feasible. In addition to this, they also satisfy the other inequalities. So these are the extreme points, these are the intersection points. So here there are 5 hyperplanes, so, and all of them are, none of them parallel to each other. So we will have 5 choose 2 intersection points. So I have not drawn some of them, the intersection of these two, the intersection of these two, and so on. Okay, so hope the notion of an intersection point is clear. Now we will further make a distinction among these intersection points. Okay, look at this intersection point. These are the two hyperplanes. Let me again draw the normal. The normal to this is this one, the outward normal, and the normal to this thing is this one, the outward normal. And look at the cost vector. This lies in the cone generated by these two. Okay, so for this intersection point, the cost can be written as a non-negative combination of the corresponding planes. Look at this one. Here also we are able to write the cost as a non-negative combination. On the other hand, look at this one. This is not an extreme point, this is an intersection point. Here look at the normal to this hyperplane, that will be this one, and the normal to this would be this one, and the cost is here. So cost is no longer, cost is not a non-negative combination. Okay. So there is something special about these points. Let's see. So define F to be the set of intersection points such that the cost can be written as a non-negative combination of the outward normals. So here it would be this, 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 and the intersection of these two. So in a more precise sense, a point X which satisfies n equalities, that is an intersection point, is in F if the cost can be written as a non-negative combination of these particular vectors. Okay, so here I am taking ai1 to be a row vector as in here, and so that's why I am using C transpose. Okay, now here is the main theorem. It turns out that the required optimum, that is the optimum of the primal here, is a point in this set with minimum cost. So let me illustrate this. So among all these points, see, first of all, our required optimum is in F because it satisfies this constraint. There are other intersection points in F, although they may not be feasible. Now among those points, it turns out that the one with the smallest value of the cost, see, if I look at this, this is the normal, okay, this is the normal to the cost. So cost increases if I go like this. So clearly the cost here is bigger than the cost here, the cost here is bigger than the cost here. So that is what this theorem says. You look at all the intersection points which satisfy this phenomenon and look at the minimum among them, that will be the required answer for the LP. Okay, so let's try to show this. So this is what we want to show. For every point x in F, we first want to show that C transpose X is bigger than or equal to C transpose X naught, where X naught is the optimum of the LP. Okay, let's try to show this. So to show C transpose of X minus X naught is bigger than or equal to 0. Okay, so firstly, since X is in F, we can write C as some alpha I1 A I1 plus alpha I2 A I2 and so on, where ai1 till ain are the defining vectors of X, and alpha I1 till alpha an are bigger than or equal to 0. Okay, now let me write C transpose here. Now C transpose of X minus X naught would be alpha I1 A I1 X minus X naught plus alpha I2 A I2 X minus X naught and so on in X minus X naught. Now what do we know? Aij of X will be Bij, because these at X we have equality for these constraints. Now what do we know about Aij of X0? Since X0 is feasible, it has to satisfy the constraint. Okay, so it will be at most Bij. So what do we get? This implies Aij of X minus X naught is bigger than or equal to 0. Okay, and since alpha ij are all bigger than or equal to 0, we get C transpose of X minus X naught bigger than or equal to 0. Okay, so you can go through this again. We have taken a point in F and we have shown that the cost at that point is bigger than or equal to cost at X0, where X0 is the optimum of the LP. Okay, now so this shows this theorem. The optimum of LP is a point in F with minimum cost. So there could be many points with minimum cost, and all those points would be optima of the previous LP. Okay. So this is the basic observation which helps us in the definition of the dual. Okay, so here is one more step towards it. Okay, now what do we have? So here we are. Suppose, so you take an X and say C transpose is of this form. Yes. Now define an m dimensional vector. Note that m is bigger than or equal to n. In our case, so here we have n. So and then there are some other rows which were untouched. Okay. Now you define an m dimensional vector as follows. So put yi1 to be alpha i1, yi2 to be alpha i2, yin to be alpha in, and yj to be 0 for all the rows that were not selected. Okay. Now clearly, yeah, so this is what I've written here. See, you can write C transpose as this plus 0 times aj1 till 0 times ajn. Okay. Now C transpose x would be alpha i1, ai1 x, ai2 x and so on, like in the previous proof. But ai1 x is just bi1, ai2 x is just bi2 and so on. And for the 0 cases, it's 0 times bj. Right? So if you just plug in x here and use the fact that this is equality, this thing, you will get this this equation here. Okay. So for every point in this set F, instead of looking at C transpose X, you might as well look at D transpose Y, where what is Y? Y is the combination that gives C transpose. Okay. So you see that we are somehow coming close to the dual. Okay. So here we are. Let's define F bar first, so that which talks about the y's and not the x's. Okay. So you take an x in F, and for each x you will have a y as here by looking at the corresponding hyperplanes and then defining this y like this. Now take those y's. So there are finitely many points in F, and so there are finitely many combinations in F bar also. So what do we have? The least value of B transpose Y among Y and F bar is the same as the minimum over C transpose X for X in F. This comes from here. And from the previous observation, the least value of C transpose X among X in F is going to be the optimum of the primal. Okay. So what we have is this equals this. Okay. Somehow we will try to now show that the dual, the optimum of the dual is actually the optimum of this, the minimum of this. Okay. Now this motivates us the definition of the dual. So what is essentially the dual here? We want to write the cost as a non-negative combination of the hyperplanes defining ax less than or equal to b. Right? Let me just write. So we had ax less than or equal to b, a1. So there are m constraints, and then we want to look at a non-negative combination of this that gives us the cost, and among them we want to look at the least value of this. Okay, so it's still not exactly f bar. The set of feasible solutions to this could be infinite, whereas here f bar we have some finitely many points, right? Now how do we link this one to f bar? Okay, so here comes the main theorem. Extreme points of dual, the set of extreme points of dual equals f bar. Okay, so this is the main observation, and now we want to prove this, but before that, what do we get out of this theorem? So suppose this theorem is true, the optimum of the dual will be the min over all extreme points. Okay, and the min over all extreme points is this thing, and this equals optimum of the primal. Note that f bar is non-empty because we have started with a primal which had an optimum, and that optimum was in f, and the corresponding combination was in f bar. Okay, so this set is non-empty and this set is non-empty, and moreover we should be able to show that plus the fact that C transpose X naught is less than or equal to B transpose Y for all Y feasible of dual. So this part, using this plus the fact that, so what does this give? This says that this thing is bounded. Okay, so bounded from below because there's a minimization problem. Then the optimum will occur at an extreme point. Okay, so the optimum of a dual will be the least value of the extreme point, and this turns out to be the optimum of the primal. Okay, so we have the duality theorem. When the primal has an optimum, the dual will have an optimum, and both the optima are equal. Okay, so the only thing that remains now is to show that the extreme points of the dual are equal to this set f bar. So before going ahead, make sure you understand what this set f bar is, and recall what are the notion of extreme points, and try to do this association yourself. Okay, so here is what I'll give you the proof of this fact. So to do that, let's first analyze the constraint matrix. So it's going to be A transpose Y, so equal to C, and Y bigger than or equal to 0. So how will it look like? So the first row of this will be the first column of A. So all these orange lines are columns of A. So there are how many columns in A? There are n columns. So you have this part is the columns of A, and these things are the rows of A. So there are m rows, so these pink lines will be the rows. Now what are these things? These things correspond to this y bigger than or equal to 0. So there are m coordinates here. So you will have this identity matrix here. So these things are 0 here. So the m cross m identity matrix here. Okay, so this is how the constraint looks like, and this multiplied by y1 till ym should give you the C followed by 0, 0, 0. Yeah, that is what this says. Okay, and we want to look at extreme points of this. So to get extreme points of this, we need to look at m linearly independent rows of this, and they have to be tight. There should be equality. So there's already a lot of equality here. Now, so there are how many? There are n equalities here. In any feasible solution, you will have equality for all the first n constraints. But for an extreme point, we need m. So you need m minus n equalities here, which means we should put some m minus n y's to be equal to 0, and then we will get some m rows, and then we have to show that they are linearly independent and so on. So let's go a bit slow here. So the first thing to note is that if I look at the first n rows of this matrix, they are going to be linearly independent. Okay, so why so? So let me read through this. So since primal has an optimum, that means there is an extreme point, there are n rows of ai1, ai2 till ain, which are linearly independent. So let them be somewhere here, ai1. So these are going to be the rows of A, right? ai1, ai2, ai3 and ain. Okay. Now look at the matrix just corresponding to these rows. Okay. This is the first row. This is ai1, this is ai2, and this is ain. Okay. So since there are n linearly independent rows, these columns should also be linearly independent, since row rank is equal to column rank. Okay. Now what do we have? So that is more or less it. So I have n columns here which correspond to the n rows of A which are linearly independent, and this statement says that the corresponding columns will also be linearly independent in that embedded matrix. This will also imply that for this bigger matrix, the n rows of this matrix are also linearly independent. So let me try to draw the. So we had some ai1, ai2 till some ain. Now if we restrict it to only the green columns, the corresponding rows were linearly independent. Now we claim that even the bigger rows, which include all the other columns here, the bigger rows will also be linearly independent. This is because if I take some combination of these bigger rows and I get 0, I particularly get 0 in these coordinates also. Right? So if some combination of them gives 0, then that same combination should give 0 in these corresponding points. But then we know that since these particular rows which correspond to this are linearly independent, they correspond to the columns of this, are linearly independent, the only combination that can give us 0 everywhere should be 0. Okay. So what do we have? The first n rows are linearly independent. Okay. So now let's go to the proof. So we want to show that extreme points of the dual are equal to the set f bar. So we will show the two directions. We will first show that every extreme point of the dual will be in this set f bar. Okay. Now, so if I take an extreme point y bar, there will be m equalities, as I said before. Okay. We need equality at m linearly independent constraints. So we already have equality at the first n constraints. So we will have m minus 1 of yi to be 0, right? So let them be like this. Let yj1, yj2 till yj m minus n, let these be the m minus 1 which are tight. The others are bigger than or equal to 0. We do not know whether they are equal to 0, strictly bigger than 0. They are bigger than or equal to 0. But we know for sure that m minus 1 of them are equal to 0. Okay. Now what we want to show is that this particular y, y1, y2 till ym, this is an f bar, is what we want to show. Okay. Now this is some statement which comes from definition, which is that in addition the corresponding rows will be linearly independent by definition because it is an extreme point. Okay. So now we want to show that this belongs to f bar. See, firstly, from the equations, from this we have that y1 times this thing, this equation, we have y1 times this thing plus y2 times this thing plus y3 times this thing and so on plus ym times this thing is equal to c, right? And these things are all 0. So we have c to be a non-negative combination of some n columns of this constraint matrix, n columns of this, but each column here is going to be a row of A. Okay, and that is what I've written here. So you can look at it as C transpose is yi1 ai1 plus yi2 ai2 and so on. So I'll write it that way. So C transpose is equal to this. So we get it. Okay, and so we get C to be a non-negative combination of n rows of A, and hence this particular y should be in f bar. If you go back and look at how we defined f bar, you will realize that this particular y should be in f bar. Okay, so this side is done. Now let's do the other direction, which is this set f bar is contained in the set of extreme points. So if I take a y in f bar, so how will it look like? There will be some n numbers which are non-negative such that C transpose is a combination of the corresponding, combination of some n rows of the matrix. Okay, and the others are equal to 0. Okay, right. So the rows corresponding to the indices will be here. Now moreover, this ai1, ai2 till ain are all linearly independent. So this is how we defined f bar. Okay, now we want to say that this particular point is an extreme point of the dual. Now the fact that these ain are linearly independent will imply that in the constraint matrix, the first n rows along with the rows corresponding to the yi's which are 0, as in this n plus j1, n plus j2 till n plus jn minus m, those will be linearly independent. So I will draw the picture in the next slide. So we have that ai1, ai2 till ain, they are all linearly independent, and there are some yi1, yi2 till yin which are potentially bigger than or equal to 0. Now yj1 till yjn minus m are the ones that are out of this. So I did not choose this in ai1, so yj1 will be chosen. This was not chosen in in the a's, in the n rows. So this will be chosen in the j's, right? So yj1 will be 0, yj2 will be 0. All the columns, all the m minus n columns which were not chosen, the variables corresponding to that here will be the j's. Okay, so this row will be chosen as long as this column was not chosen. Okay, now what do we know? These are all linearly independent as columns, so the corresponding rows will also be linearly independent, right? Now finally we want to show that these n rows along with this row, the rows corresponding to j1 till jn minus m, all these m rows are linearly independent. Suppose I combine them, alpha 1, alpha 2, alpha n, then alpha n plus 1, alpha n plus 2 till alpha m, and I get the 0 vector. It will have dimension m, 0, 0, 0, m times. If that is the case, you look at just this part, the rows, and just look at the rows. See, here it is going to be 0. In no j, in no row corresponding to the j's do we have a non-zero component here. Okay, similarly for this also, in all the j rows it will be 0. So if some combination of them is giving us 0, then this combination is already giving 0 for these columns. Okay, which will imply that if I restrict to only the green part and look at the rows, they will be linearly dependent. Okay, if any of them is non-zero. So this will, but that is not the case. So all of these alpha 1 till alpha n will be equal to 0. But then this one, everywhere else in all other j's it is 0. This will imply that even alpha n plus 1 is 0, alpha n plus 2 is 0, and so on till alpha m is 0. Okay. Just use the fact that these are linearly independent, hence the corresponding rows are linearly independent, and we are choosing the j's which do not correspond to these indices. Okay, and using this fact you will be able to show that the rows corresponding to our choice in the constraint matrix will be linearly independent, and moreover this feasible solution comes with equality on those particular rows, and hence it will be an extreme point, and that shows that each y and f bar will be an extreme point of the dual. Okay, so this way we have shown both directions, and this gives us this theorem: the extreme points of the dual equals f bar. Okay, and from here we got the duality theorem. Okay, the optimum of the dual equals optimum of the primal. Okay, let me just try to summarize. So what we did, given the primal was of this kind. Given this primal, we looked at all the intersection points, that is the points with, you choose n hyperplanes out of A, n rows, and then intersect them. You don't care about the other constraints. Consider all the intersection points such that cost is a non-negative combination of the rows corresponding to our choice. Okay, and we have shown that the optimum of the primal is a point with the least cost in the above set. So this set was f, and the optimum is a point with the least value of C transpose X in f. And from f we defined f bar, and from f bar we defined the dual. So from f to f bar, how did we go? For each point x, we looked at the actual value of the combination that will be, and for the rows that were not chosen we put 0 and we got a y bar, and that gave us our f bar, and we showed that optimum of primal equals the min cost in f, which was equal to the min value of B transpose Y in f bar, and from there we just had to say that in the dual the extreme points equal f bar. Okay, so this is a kind of a geometric interpretation of duality.